let us revise briefly. How does it work in that case, right? So you see, in this context, we are considering a finite dimensional system in n dimensions, the control being in m dimensions. But the same will apply if we were dealing with an infinite dimensional dynamical system. The Schrodinger equations, wave equations, heat equations, Stokes equations. Okay. So we are given an initial datum, and we know that the controllability of the system is guaranteed when A and B fulfill the Kalman rank condition, right? So remind you that the Kalman rank condition is that the rank of B, AB up to AN minus 1B is equal to N, right? And this is related to the theorem of Cayley-Hamilton, which says that once you know all these powers of a matrix, A to N, AN minus 1, identity A, AN minus 1, all other powers of A can be derived out of this, you know, combination of these lower ones, right? And behind it, there was also the power series expansion for the exponential of A, which is the generator of the semigroup and so on, okay? Well, so the first thing we should say is that this, if the system is large, I mean, you are dealing with a large system, I don't know, the human cardiovascular system, the human brain, or a social network, N is huge, checking this algebraic condition might not be easy, right? So one thing is that, you know, the formulation algebraically, analytically is very easy. And another one is the computational, the computational complexity, okay? So that's a wording here. So here, this leads to high computational complexity. When N is large, okay? Good. Okay, so then what is the prototypical goal in control theory? In principle, open loop control. So we are here doing open loop control, right? So I am interested on open loop control. We have the other day also shown how once you have done the open loop control, you can build feedback controllers, right? Which are in that sense much more realistic because you can compute the control on real time out of the state. But this is the central problem we have to understand in order to then, you know, derive all the other conclusions is this prototypical problem of controllability. So we are given a time horizon, we are given an initial datum, we are given a target, a time capital T, and we like to build the control so that xt is equal to xt. And we said, in order to do this, it's very interesting to look at the adjoint system that now is solved in the opposite sense of time. So time goes from capital T to 0, right? And it turns out that once you understand or you employ the adjoint system, being a successful control, U can be written by duality. So we are just using the solutions of the adjoint system as test functions in order to multiply in the state equation and integrate by parts. And what we realize is that, you know, this identity here completely characterizes being a control, right? Why? Because when I multiply the equation of the state by phi, right here, I will get bu phi, or if you want, u b star phi that you integrate from 0 to capital T. So you get this term here, right? And on the right-hand side, the only thing you get is the terms associated to the integration by parts in time, right? Between x prime and phi, right? Why? Because once you integrate by parts, and you put, you know, the a of x into the a star of phi, again, by definition of the adjoint. So ax times phi is simply x times a star phi. And you use the adjoint equation, then all this contribution is gone except for these, say, extremal terms, t equals 0 and t equal capital T coming from the integration by parts here. And therefore you get these two terms. So you see that here, x0 is given, is the initial datum of the system. xt is given, is the target we are given, right? U is the control we are looking for, and phi is an arbitrary function, right? Solution of the adjoint system for every phi t, okay? Then the next step was to realize, oh, but then, you know, this is the Euler-Lagrange equation for the minimization of this functional. Indeed, if we are able to minimize this functional, the critical point of this functional leads to the control U, right? The control being simply U equal to B star phi hat being the minimizer of phi t. The existence of the minimizer is guaranteed by the direct method of the calculus of variation because the functional is quadratic, is convex, is continuous in a Hilbert space, in Rn, actually in the Euclidean space. The only tricky aspect is to prove the coercivity, but the coercivity is guaranteed. So the coercivity of J, is equivalent to the observability inequality, right? Which guarantees that this inequality is true, right? And this is equivalent to AB fulfilling the rank condition, right? Okay. And this observability inequality here, right? This observability inequality here, right, is also something that for a complex system, it might be not so easy to somehow analyze, treat, understand, right? So again, if the system has a very large dimension, you can think, for instance, of the network of fast trains in China, right? And then you can put all the, you know, this will be like a planar network with significant nodes, like in the biggest cities, many different lines, you know, going in different directions, connecting each other. This will give you a quite complex planar graph. And now you think on information flowing along this graph, right? You know, determining what is the proper B star, right? So what are the nodes you need to observe in order to recover full information on the system can be something quite complicated. As you know, actually, one of the most relevant algorithms in internet is the Google page ranking, right, algorithm. And this originates from a very simple mathematical idea. So you know that Brin and Page, that were these two young fellows from, in particular, I think the University of Maryland also. They studied computer science and then they started developing the Google search engine. So of course, as we know well, one of the key, say, features of these search engines is that when you will, you know, look for, you know, you Google a given, I mean, the other searchers are also inspired in the same idea. So I'm talking about Google, but it could be any other web browser engine. So when you write a name, right, or a keyword, the computer will show you a list of locations, persons, right, whatever you are looking for, but ranked in an order, where in principle, you know, in the first position is the, you know, is the person or the place you are looking for, right? So for instance, if you write Einstein, you will certainly get Albert Einstein, right? Why? Because he's the most celebrated person ever in the history of humanity. Is one of the most celebrated ones, right? But certainly with the name Einstein, you will have this one, right? Why this one? There are many other Einsteins, right? People that are still alive and have the name of Einstein, and they they are doing all kind of different tasks. There are streets in different cities with the name Einstein. There are hotels with the name of Einstein. But when you look in the web, you will not get all these secondary, right, locations or persons, right, associated to that name. You will first get Einstein and then the others, okay? So the question that Breen and Page analyzed was, okay, given a very large graph as internet is, thousands of million people linked each other, sending emails, looking to the web pages, one or the other. So I look to the web page of the Jinling University, right? And I go to mathematics, and then in mathematics, I go to the web page of Professor Kai Zhang and other professors, right? So this is a huge network in which thousands of millions of people are linked each other, right? Then the question was for them, how out of this, say, large network, thousands of millions of nodes, right? If you put them on a plane, this will be thousands of millions of nodes. You could write this down in a matrix capital A, right? And say that the information flows on this system, right? Following this kind of principle, dynamical principle that, the activity of each node, right? In which direction this activity is pointing is really related to the connectivity, right? And the evolution of time. Then you will say, oh, fine. So this is a, this is a linear dynamical system. Yes, but the problem is that the dimension n is huge. It's thousands of millions of individuals, right? So then even very simple questions like check the Kalman rank condition is something that you will be unable to do, right? Not even with the computer, with the aid of the computer. But for them, there was another basic difficulty. It was, what is really the model you put onto this system? So it's true that we have internet and there is some, interlink between the different nodes, but how are they really related? I mean, you cannot really monitor on real time the whole flow of information in internet on a deterministic manner. It's always even if the average time each of us spends on specific web pages, like checking the web page of the local newspaper or reading mathematical articles in the web page of SIAM or American Mathematical Society, of other journals, etc. How much time you spend on the web page of your own group, working on it, or even if you have this kind of average information, you cannot really anticipate what is the actual behavior in real time of the system will be. It will be something that is very noisy, very stochastic, right? With a lot of uncertainty on it, right? So they said, what is the dynamics we have to put? Well, it's very complicated. We don't know. So, but they said, well, but we know from physics, right? Einstein was one of the contributors to this, right? Main contributor. That in the classical context of mechanics, when particles are moving in a Brownian manner, right? Eventually, you converge to a Gaussian diffusion process that is governed by the heat equation, right? And they said, well, let us think on this. So the internet network graph is so large, so complicated. The behavior of people on internet is so hard to anticipate that let us think this is a Brownian motion. So then the model I should write is the heat equation on a graph, right? So we will come back to PDEs on graphs later. Okay, then if you write down the PD, the heat equation on a graph, again, I mean, this is a partial differential equation on a huge graph. It will be impossible to model and simulate this, right? But you say, well, but I know that as time goes to infinity, the solutions of the heat equation on a domain or in a given manifold domain or graph, right? They behave essentially according to the first eigenfunction of the Laplacian. So they said, okay, let us consider what is the first eigenfunction of, of the internet graph, right? And then they realize, oh, but the Laplacian, the discrete or continuous Laplacian on a graph is a self-adjoint operator fulfilling the comparison and the maximum principle. And according to Perron-Frobenius, the first eigenvector has all positive entries, right? And therefore, because if I normalize the eigenfunction to 1, every entry of this eigenvector, the first eigenvector, right, which is just what is the value you allocate to every node in this huge network, will be a positive number between 0 and 1, and this will give you the ranking, right? So the ranking comes, at least originally, from this very principle that it is very hard, right, to analyze questions like the ones here, right? This will be very similar. So page ranking is not so far from these kind of questions, because in these kind of questions, you are trying to determine what are the nodes, right? What is the B star? What is the projection? What are the nodes in which you have more information about the behavior of the system? You see that this is very similar to the kind of questions you address in PageRank, where you try to identify the most important nodes, right? These questions, although analytically beautiful, elementary, and totally equivalent to the original control problem, can be hard to address fully in the practical application. And oftentimes people have to give up a little bit and relax the condition, for instance, through this principle of Brownian motion, and then going down just to one eigenfunction to get something operationally, practically implementable. Okay, very good. Okay, so this is what the theory says. The control can be computed that way, right? So now, how does the algorithm read? We mentioned that the other day. So now, if you ask me, you have to minimize this functional, right? You have to minimize this functional in Rn. Right, so this is the task I have to fulfill, minimize this functional in Rn. Then the first comment I would like to make is that there is something magic on this, right? Why? Because in principle, I was looking for the control U. And the control U, recall, right? The control U belongs to L2 0T with values in Rm. So the control U lives in an infinite dimensional space, huge, a very complex problem, right? So this is the control U. But in fact, in practice, thanks to this adjoint methodology, and this is one of the important applications of the adjoint methodology, thanks to the adjoint methodology, in order to compute the control, you just need to work in the space Rn, which is finite dimensional, for the initial value at t equal capital T for the adjoint. So you see, you have reduced significantly already the complexity of the problem. I don't work anymore in the infinite dimensional space of the controls. I just work in Rn. So that's great, right? As a simplification of the problem. And then once I have to look for the state phi t in Rn, the only thing I have to do is to iterate according to the gradient. So what do? We say, okay, I will build an iteration to compute the optimal phi t as a limit. I initialize in some given manner. If you have any guess, right, you could take, for instance, as phi t, an initial value for phi t, you can take here 0, You can take the one eigenfunction of A star, right, which is certainly relevant for the dynamics. Or you have done previous computations in similar problems. You could simply adopt, you know, the initial datum you have achieved for a different, say, problem as phi t. Note, for instance, that of course, you know, in this functional, the functional has a quadratic form, right, which is universal. It simply depends on A and B. But for instance, the functional does actually depend on x0 and xt, because of course the control that has to bring from one point to another depends on the origin and destination. But for instance, if you have already minimized these functional ones, even if you change the initial data to be controlled, you can maybe initialize the process with the minimum given by, you know, the other data, right? In any case, so you have to initialize, right? And you do it the best you can. And once you initialize, then the only thing you have to do is you iterate, right, from phi k to phi k plus 1, always, you know, talking about, so all this is always happening in Rn, right? So you are moving from, right, one guess that I have for the value of the adjoint at capital T into the following one, following this, say, gradient rule, according to which we have to go down on the value of J. We are going down and down and down on the level sets of J, pointing in the direction of the gradient, okay? So we know that rho has to be small. We know that you know, we have said the other day that in principle, we have proved the gradient steepest descent algorithm with a fixed rho. But then there was very interesting questions about whether I cannot take the rho to be depending on K. And of course you can, because we have seen that this is related to the Taylor expansion, power series expansion of J. And therefore there has to be a compromise between the gradient of J and the Hessian of J, right? There are many variants for this. Very often you have very weak information on all these constants like gradients and Hessian when you are working in high dimensional spaces. So you often also use the simple rule that you take a rho relatively large, right? But if you think, if you see that the functional J is going up, then you will divide the rho by 2, right? So this is something that may happen when you are doing some, you know, more heuristic search of the rho, right? So if this was the functional you were considering, right? If this was the functional J, and this is the state, this is the space of the phi t's, right? So maybe you start with an initial guess over here, right? Where you are there, then the gradient descent algorithm will tell you to come here to the right. And then again, you will come here to the right. And then again, here, you will come here to the right. Of course, what is the risk? The risk is that if the rho, if the step rho, the width on which you are jumping from one to another is too large, right? You can go here and you are not going down anymore. Maybe you are going up again, right? So oftentimes, the way to choose the rho is simply heuristic. You try to, you know, advance with a significant rho, because in this way you go faster towards the destination. Of course, you know, here we have gone from this point to this one in 2 steps, but I could have gone also in 1 step if I have taken rho larger, and this reduces, of course, the computational cost. This is something we will analyze now. We discussed that the other day too, but I will revise it now. How much you spend computationally on each step of the gradient iteration. This is why in practical applications, you will try to take rho large, be ambitious, and then say, oh, if I take rho large in this step, and I see, right, the test of whether, so you see there is only one test in this problem, right? Is this rho good or bad? It's very simple. The only thing you need to check is whether rho phi at the new step is smaller than rho on the previous one. If this holds, the choice of the row is correct. If, of course, for any reason you went too far on row and then you are up again, this is that the row was too large. Then what you will do, okay, if row was too large, I divide by 2 and then do a shorter step and then I check this condition again, right? So then in practice, you can also do heuristic arguments in order to find the optimal row, right? There are many versions for this. But the geometry of the problem is very simple, right? In particular, because here we are in a convex configuration in which there is only one minimizer and the minimizer is known to exist, right? Okay, good. Very good. So then what does one step on the adjoint resolution mean? So when you check, this is the way the problem looks, right? We have said that an optimal control is given by a solution of the state equation where the control is B star phi, right? With the initial datum x0, phi being a solution of the adjoint problem, and the final datum phi t, right? And of course, you can solve this system, right? You see, given phi t, I can always compute the phi. The solution phi of the adjoint system is independent, so I can always solve this. I can come here and I can also solve now this equation forward, right? So this equation is to be solved forward. This equation is to be solved backward. So I can solve this equation and this one for any phi t and x0. This is not a classical Cauchy problem, right? So in a Cauchy problem, if I would like, someone could think, oh, let me try to, you know, Enrique is writing a strange system because I have for x, I have, you know, x doing something like this, right? And for phi, he has put a minus sign, but I like to put it correct, right? And then you could say, oh, but then if I introduce a new variable, capital P being x phi, then I can write this system as d over dt plus times p, and then a matrix operator, sorry, it should be a 0 0 minus a star, right, of p equals something. I could try to write this as an ODE pointing forward in time, right? And indeed, this is something I can do. I can algebraically see this equation and this one, both two components of a Cauchy problem for a single system of ordinary differential equations. But this will never become a Cauchy problem because for x, you have the initial datum at x0, right? And for phi, you have the initial datum at capital T. You could say, well, but this is not such a problem because here I could make a change of variables. You can try everything, but this will not work, right? I could also do the change of variables from T into capital T minus T to make this terminal condition at time capital T to be an initial condition at t equals 0, and then try to make this to be a Cauchy problem. But you will not get it, right? Because then there will be a link here between the state x at time t and the state phi at time t minus t. So you will have apparently a Cauchy problem, but this will not be the Cauchy problem because the coupling between the two components of the equation will not be at the same time instant, but in two different times. So there is nothing you can do. This is not a Cauchy problem, right? But if you really ask me to solve this, I tell you no problem. But clearly, even though the equation is written so that the system is written so that first you write the state equation, which is the one you are interested, and the adjoint is just an auxiliary system, right? In practice, I will solve it in the reverse order. So I first, given phi t, I solve phi because phi is independent. And then once I have phi, I plug phi onto the right-hand side. This becomes a given non-homogeneous datum. And then I can solve the forward system for the state equation, right? And then what is the successful phi t? The successful phi t is the one that makes that we achieve the terminal condition xt on the state. That was really the goal. I think we are using the notation here, phi t down. Okay, good. So all the question is, how do I find this magic phi t that will guarantee, right, that my goal, right, this is the goal. How can I find the phi t that guarantees that we fulfill the goal? We said we do this gradient iteration and that's it, right? But then, you know, in practice, if you are a practitioner of this, I mean, this is very simple to program, right? Going from phi k to phi k was 1 is just a line, a command line. But well, you have to say what the gradient is, right? So the key, you know, on the application of this gradient descent is always the computation of the gradient. And this is something that is tricky, right? Because you see, if you think on, you know, what is the gradient? Yeah, so you think on what is the gradient of J at a given realization in time, you know, in a step K of the iteration of the gradient descent. If you ask what is the gradient, in principle, of course, the gradient of J has n components, right? Because phi belongs to Rn, right? And therefore, phi t has n components, phi t1 up to phi tn. So if you ask me what is, you know, the gradient of J, then you will have to compute the derivative with respect to the first variable up to the derivative with respect to the last variable. And again, you know, you encounter here the course of dimensionality. You say, well, I mean, of course, intellectually, computing partial derivatives is very simple. It's just the limit of a, you know, of a incremental quotient. Yes, but when you have to do n of them, and this n is of the order of neurons in the on brain or users of internet, this is really impossible to achieve, right? So is there a way of making this computation of the gradient simpler, more, say, systematic, computationally less expensive? This is also something very, very important in the theory of optimization and control, is computing the gradient. Mathematically, there is no difficulty. We know the concept of Gateau derivative, of Frechet derivative. We know how to define the partial derivatives. The issue is to compute them, right? And actually, if you remember, in one of the first classes we gave in this series of lectures, we mentioned some of the most fundamental algorithms in the history of scientific computing. And one of them was automatic differentiation. Why? Well, because we really like the computer to learn how to do this in a quick manner, an efficient manner. So what does automatic differentiation do? Well, automatic differentiation does what we do when we think on differentiating a big function, right? So how did we learn how to differentiate? I mean, you know, the principles were always the same. The derivative of a polynomial, oh, that's very simple. The derivative of the exponential, that is very simple, it's itself, right? The derivative of trigonometric functions, okay, fine, very simple. The derivative of a quotient of two functions, okay, very simple. And then there is a super powerful tool in differentiation theory, which is the chain rule, right? We learn how to differentiate the composition of two functions. So in this way, whenever you give me a function, I know how to differentiate, right? If you tell me that I have to differentiate the logarithm of the sinus, of the cosinus, of the square root of 1 plus x over, I don't know, 3, then you know how to do it. You just apply the chain rule, multiplying derivatives one after another, and then you know how to compute the derivative of every single piece, because these are basically elementary functions and you have learned how to do that. This is what automatic differentiation does for us. So automatic differentiation will take the code you have written, you know, in MATLAB, Python, or Fortran, or wherever. It will take this code, and out of this code will generate the differentiated code, right? In which you simply, you know, the code says if there was a link between one variable and the other, right? If y on the code was equal to x squared, in the differentiated code, the y dot, you know, the increment of y, the new variable, you know, delta y associated to y after linearization will not be anymore x squared, but it will be 2x, x coming from the original code, times delta x, which is the new variable associated to the variation of x. Okay, so you will be able to do out of a code, you know, computational code, the automatically differentiated code. Okay, so this is something very important in practice. But there is still, you know, some work to be done at the analytical level. What's that? Okay, let's compute what the gradient of J is. The gradient of J, of course, is a vector. We have to compute directional derivative. So you give me any psi t in Rn, psi being the corresponding solution of the adjoint system, right? Psi will be the solution of the same adjoint system out of psi t, right? When computing the derivative of the quadratic term, of course, I will get the crossing here of bi star phi and b star psi. And then the linearization, I mean, the differentiation of the linear term is trivial, x0 and xt are fixed. And I will get here simply psi t and phi 0, right? Fine. On the other hand, when you say, what is, you know, what is b star phi times b star psi? Well, you see, if you ask me this, I will tell you, listen, if phi, because phi is plugged into the equation here, if you ask me what is b star phi and b star psi, the product here, this is like coming here and multiplying by psi, right? I see there is some delay. Okay, so it's like, because phi is plugged on the right-hand side of the state equation, if you ask me what is b star phi times b star psi, is like multiplying here by psi, because the b here will come onto psi as a b star. So it's like, again, multiplying here by psi and integrating on time. But the classical, you know, adjoint calculus will tell me the equation will go away, and the only thing you will get is the crossing at t equals 0 and t equal capital T. So you see that eventually this multiplication is just that. And then you say, oh, but then this means that all this complicated term here on the gradient, together with this difference at t equals 0 and t equal capital T, simplifies to say that the gradient of j phi t is simply xt minus xt. In other words, and this is the key point, right? The gradient of j is simply the residual of the control requirement. So you see, my goal was to drive xt, x at time t to xt, and precisely the gradient of j is the residual, is the error I have made when I didn't yet reach to the start control. But this is also natural. Why? Because we characterized being a perfect control as being a minimizer of capital J. If you are a minimizer of capital J, the gradient of J is equal to 0. And then the residual is equal to 0. So it's very natural that the residual, right, is to be, right, is to be related to the gradient. Actually, they are identical. And once you realize that, right, that the gradient is just given by this residual, you realize that the algorithm for the gradient steepest descent iteration, it simply reads that way. Oh, magic. You see, eventually, I don't need to compute the gradient of J because I know what the gradient of J is, simply this. So then you see that the algorithm becomes very, very simple. It tells you, what do I have to do in each step? Well, it's very simple. Out of the value of phi you have at the step K, first, you solve the adjoint equation backwards in time. Of course, the adjoint equation is always to be solved backwards in time, from 0 to t. This is the first step. The second step is you take this phi, K, now you plug it on the right-hand side, and you solve this equation forward, right? And then, you know, this is the gradient algorithm. You simply compute the distance from the point you got to the target, right? The distance from the point you got to the target. If this distance is small enough, this is also a stopping criterion for your gradient descent algorithm, right? Because you say, well, in practice, I was requested to guarantee that xkt is equal to xt. Okay, but I give myself some error, 10 to the power minus 4, for instance, as an error. If this error is already small enough, I stop the process, right? It doesn't make sense to, you know, to continue working. I have been writing these notes. Of course, my handwriting could be better, but then I will devote a lot of time. Maybe this is sufficient, right? So the error is sufficiently small so that I share the notes with you, and they fulfill the purpose of enhancing communication and then your revision and so on, right? So if this residual is small enough, I stop. And if the residual is too big, I make one further step. But I know which direction in which I have to move is. So you see that eventually, you know, this becomes like magic, because the goal was to find a control in an infinite dimensional space, U. Through the adjoint methodology, we have reduced the problem to minimizing a functional on Rn for the adjoint. Yet this can be tricky because you have to apply a gradient descent algorithm and in every step compute the gradient of J. But magic, in fact, there is no gradient to be computed. It's just a concatenation of solving the adjoint equation and then the state equation, right? So in every step, you are simply concatenating the resolution of first the adjoint equation and then the state equation. And you see that this is important. The order is first the adjoint and then the state. It is curious, right? Because in principle, our unique goal was to deal with the state equation. Nobody told me about the adjoint equation. The problem is formulated on the physical model. I have this physical model for conduction of electricity, distribution of gas on the network, or internet, or social opinion, you know, whatever you have in mind. My goal was to regulate the dynamics of this system. I'm not interested on the adjoint system. But if I know that there is such an adjoint system, I can do everything through the adjoint. In particular, I can test the controllability out of the observability condition, and then I can build the iteration leading to the control, right? So that, you know, what is the actual control I will use in practical applications? I will use a stopping criterion. Will be that x t minus xt is less than epsilon with epsilon positive given, right? And once I have done this, the control I will take will simply be b star phi k, right? So I do as many steps as they are required in order to reach that the residual is below the given threshold. And once I achieve this, right, then this will be the control chosen. So you can see everything on the adjoint, right? And in the iteration of the gradient methodology, you will first solve the adjoint system and then the state equation. Okay, very good. So then, as we have said, there are many variants of this steepest descent algorithm, right? One of them is that you don't need to do rho fixed according to the theory. You can take a rho key rho depending on k, optimizing or even making it more heuristic. There are also methods like the conjugate gradient method that, as you know, converts in n steps. If the n is the dimension of the system, the conjugate gradient algorithm converges to the exact minimizer in n steps. So this is very nice for low dimensions. For high dimensions, this is not that nice, right? But n, as I said, in internet, n will be thousands of millions, right? So you don't want really to make thousands of millions. Actually, the power of this methodology is that, you know, in just a few iterations, 3 or 4, the algorithm descends, goes down very, very fast, and you get very close to the minimizer in just a few iterations, right? There are other interesting, very interesting versions of this algorithm are the multi-step algorithms, right? So this is like, this is a very classical variant, right? You say, I move from phi k into phi k plus 1, always in the direction of the gradient, but this time on the previous step. So this is a 3-point algorithm, right? I don't move from k into k plus 1, but I use k and the past iteration k minus 1 to go to k plus 1. So how do you think I can analyze the convergence of this algorithm? What would be your recommendation if I had to analyze the convergence of this algo? How could I analyze this? So let me discuss this briefly, right? So if I do the 2-step algo, so the 2-step algo is phi k plus 1 equal phi k minus rho gradient j phi k minus 1. So let me consider the case where j, you see, in order to understand these algorithms and the convergence, you can follow the principle of von Neumann, right? When you know, von Neumann was establishing the foundations of numerical analysis, the same he did for partial differential equations, numerical analysis for partial differential equations. He said, well, you can think on linear problems and then use Fourier analysis, right? So here we can do the same. We can say, well, so you see the J is what? The J has the structure of quadratic plus linear form, right? So the J is simply like a quadratic form, right? If I simplify the notation, minus a linear form, right? And then when J is quadratic like this and M is symmetric and positive, as it is our case, then it turns out that the gradient of J is just the matrix. So the gradient is just the matrix itself. And then the matrix M, right, can be decomposed into eigenvectors, right? And then if I look to the gradient in each direction of the space given by the canonical basis of eigenvectors, then the gradient of J is like just, you know, a positive eigenvalue. So the question that, you know, I am being asked is, can you please discuss the convergence of the iteration xk plus 1 equal xk minus rho lambda, because gradient j is lambda, times ak minus 1, xk minus 1. So is it true that for rho small, is it true that xk converges to the fixed point, right? Is it true? What will be the fixed point in this particular case where the gradient of j is equal to L, to lambda? Well, in this case, a fixed point will be simply the 0, 1, right? So I take here 0, 0, 0 is fine. Okay, so how can I show the convergence of this? You know, this is a two-step discrete dynamic. So rho lambda, I can call it mu. And you are asking me about the convergence of this. You know that the convergence of this is guaranteed. How do I compute the convergence of this? How was? I think we claim that x will be simply a to the power k, right? And then the question is, how do you find the a, the basis of this exponential sequence? And you see that when you plug this ansatz x equal xk to be a to the power k, then you will have here ak everywhere that you will remove. And then eventually you will have here this equation. But this equation is very easy to solve, right? Because this is this, right? And then this equation tells me that a is minus b plus minus the square root of b squared is minus b plus minus square root of b squared 1 minus 4 mu divided by 2. And what do we need in order to guarantee that xk converges to 0? The only thing I need to guarantee is that the modulus of a is less than 1. So is the modulus of a less than 1 here? Well, let's see. I think we can guarantee this to be the case when 4 mu is less than 1. Because when 4 mu is less than 1, then this number is positive, but it's smaller than 1. So I have two roots. The positive one will be less than 1 because this is 1 plus something smaller than 1 divided by 2. So I get a positive number, but definitely less than 1 because the numerator is less than 2. And the other root is with the minus sign, right? And then I have 1 minus a number which is smaller than 1. And this is then smaller than 1 divided by 2. This is actually smaller than 1/2, right? So then, right, I have the convergence, the exponential convergence to the minimizer. So this is the way you can analyze all these variants of the steepest descent algorithm. The condition, of course, there is a condition. The condition is 4 mu less than 1. But what does it mean 4 mu less than 1? It means that, you know, this is equivalent to mu being less than 1/4. But what is mu? Mu, we said, was rho lambda. So this means that the step rho has to be smaller than 1/4 over lambda. But this condition is very similar to the one we had on the smallness of the step for the gradient iteration, right? Because in that case too, you recall, the rho had to be smaller than alpha divided by m, where alpha divided by n was the condition number of the quadratic function, alpha being the coercivity and capital M being the upper bound on the C2 constant, right? Okay, so actually here there is an exercise you can try to do, right? Show that with an appropriate choice of the step rho, the two-step gradient algo converges faster than the steepest, this is a good exercise, descent algorithm, right? So you see that in this variant here, right, this produces an acceleration of the convergence of the gradient algorithm, right? And you see that the complexity of that will be very similar to the one, right, we have analyzed so far, right? Of course, this obliges you to keep in memory, right, from the perspective of the memory, in every step, of course, you need to know what is phi kt in order to compute the solution of the adjoint system. With the solution of the adjoint system, you solve the state equation. With the state equation, you compute the residual. And then you have to step, you know, to compute the next phi k plus 1 out of phi k plus the residual. Once you do that, you can erase your phi k. So in this algorithm, of course, you will need to keep the phi k up to the next iteration because you will use it again, okay? So from a memory perspective, you have to think that, okay, this is accelerating the convergence, the computational cost is the same, but you will need to keep two adjoint states in your memory. What are other variants? Oh, there can be also two-grid algorithms. We mentioned that the other day. What does it mean two-grid algorithm? It means that, you know, in practice, here I am discussing everything at the purely theoretical level, right? But when I come to practice, I have to solve first this in every step of the gradient iteration. I have to first solve this adjoint system backward. Solving it backward, except in very simple cases where the solution can be given analytically, it means applying some numerical discretization algorithm for the time derivative of phi, right? So you have to apply a Runge-Kutta or Euler method or whatever, right? You have to do that numerically. And therefore, right, if you do it that numerically, you need to introduce some delta t, right? And then out of this solution, then again, you will have to do it also numerically here with a delta t. You will never solve the full ODE, you will solve only the numerical discretization. And then if you recall what we said, in the gradient descent algorithm, we write it down with the gradient because the gradient is the steepest descent. But in order to guarantee that the algorithm descends, you don't need to point in the direction of the gradient. Any direction which is close to the gradient will do it. Then you see that you can play with combining two delta t's here. For instance, using one that is fine for the resolution of the dynamics that you want to compute carefully. But for instance, for the computation of the adjoint, you can use something that is not so demanding. This means that you can take here, right, in the two-grid algorithm, these ideas were popularized by, right, Ronald Glovansky, right? You can take the time step to be larger, and then rather than taking delta t, you could take delta t tilde, which is p times delta t, p being an integer number, could be 2, 10, or 50, right? Okay. You lose a little bit precision, but you will also gain a lot on at the level of the computational complexity, right? There are also, you know, methods like the random batch method that is traditional also in statistical learning. Also, you know, recently it is being implemented by Professor Xi Jin in Shanghai and his group on computations of large, you know, nonlinear dynamical systems. The idea being that, well, when you know, the system here, right? If the system here is huge, right? If the matrix A is very, very large, you can apply some splitting algorithm, and then, you know, other than doing the traditional, say, time splitting, which is fully deterministic, and that can be expensive when the size of the matrix A is large, you do some random choice of the splitting, kind of Monte Carlo way, so that you reduce, right, the algorithmic complexity of the model. So these are, you know, arguments related to splitting and Monte Carlo. Okay, this is again in order to reduce the complexity. Very good. So this was the revision I wanted to do of the gradient descent algorithm. Now, before we stop for a short break, let me tell you how in practice people will rather do, right? In particular, when, you know, computational scientists that are not mathematicians are looking to these problems, they will say, oof, all this about the adjoint, the observability, the, you know, the Kalman rank condition, all this is very complicated. You know, we need a much more straightforward, you know, procedure in order to control the system. And people say it cannot be that difficult, right? In fact, we know it is. Because once you go through all this, you know, material we have presented, you know that then in practice, actually, you will face very challenging issues, like, for instance, choosing what is the sensor, what is the bead, what is the actuator. And you have to do that in order to fulfill the observability requirements of the system. And this can be very, very tricky when you are facing particular applications. This is a critical issue, right? So the planning, right? So this is like when you design a new city, where you are putting the schools or where are you placing the hospitals, right? So these are strategic decisions, the same at the level of control. But it's true that very often when practitioners, right, in different fields of engineering, for instance, need to use control theory because there is a process to be regulated, they will try to make it in a more straightforward manner, right? So how will you approach the problem computationally if you didn't know anything about this Kalman rank condition and so on? How do you do it, right? This is the system. And the question is, compute the control. This is your only goal, right? And then you are said, well, you know, there is all this business of the adjoint methodology, but well, this is too complicated for you. You don't know it, right? This requires, you know, checking the Kalman rank condition, right? This is very complicated for systems where the dimension is very high, you know, who is able to compute the rank of B, A, B, A, n minus 1B when n is 1 million variables, right? The same happens for the theory of PDEs that are infinite dimensional systems. And actually we understand through PDEs that the Kalman condition has a very different manifestation for one PDE than the other. For instance, parabolic equations or wave equations, right? Someone could also criticize that the theory we have developed is, you know, limited to linear problems. Well, this is true to some extent. Of course, my presentation was about linear problems, but of course, I could always use these techniques in the nonlinear context, right? How do you do it? Well, you give me a nonlinear system. You give me the state you would like to reach as a target. I will linearize the system around that state, and then I will apply the linear theory. So in fact, using the classical principle that linear plus nonlinear perturbations, which is just implicit function theorem or inverse function theorem, that, by the way, is just a consequence also of the Banach contraction principle. So linear plus small variations allow you to do nonlinear, at least locally, right? And once you know how to do that locally, then you can glue pieces to make it also global, right? So even though in principle it's true that the methodology I have introduced could be criticized to be limited to be linear, I could argue this is not the case. With these linear foundations, I can build nonlinear perturbations, then glue nonlinear perturbations, and I will be able to do nonlinear control as well. Okay, but of course, this requires much, mathematical, analytical understanding of the problems, right? Okay, and then one of the reasons why these methods are not really so often applied is simply that the practitioners that are dealing with the applications simply don't know the methodology. So they will not do it not because it's too complicated or cannot be applied. They will not do it simply because they don't know it. Okay, how most people will proceed? Okay, let's see. This is our goal. We have this system. We know the system. You know more or less the system. Of course, you have to identify your system. This implies a lot of, knowledge. For instance, in meteorology, the systems for meteorological, prediction have improved along years. So we know systems very well. We know the initial state. We are able to measure the state of the system now. And the goal, right? This is the goal. I like to get there, right? So this is the goal. But of course, in order to achieve this goal, I have to identify the control. How do I do it? Well, I cook now a completely different functional. There is no adjoint here. In my world, there is no adjoint. I don't know about the adjoints. I simply say, in order to do this, I will minimize this functional with a given number k positive, right? We will discuss this later. So you could take, for instance, k equal 1. If you take k equal 1, you will have a functional to be minimized is 1 over 2 the integral of u squared plus 1 over 2 xt minus xt squared. My claim is that if you are a practitioner and you are doing control theory, this is a very nice thing to do. It's very natural. You minimize just this functional, right? Of course, this time, you see, you will be minimizing in the full space L2 of Rm. Now you are minimizing in an infinite dimensional space. You are not minimizing in Rm. Now you are minimizing in the space of the controls. It's infinite dimensional, right? Okay, first warning. You have done very naively. You don't need to know any mathematics, any adjoint methodology. The first price you pay is that because of your lack of understanding, you have to search for the control in this infinite dimensional space. Of course, searching is more complicated when the space is bigger, right? Okay, this is like, when you have lost something and you have lost, oh, I lost my iPhone. I know the iPhone is at home. Well, okay, I know I will find it, right? Maybe it's my living room, maybe it's in the studio, maybe it's in the kitchen, maybe, okay, I will find it because, I know it's in my apartment. If you say, well, I lost my iPhone yesterday, and yesterday I was in the office, I was on the metro, then I took the bicycle, then I was at home, then I went to a restaurant, then it's much more complicated. So if you have to search in bigger spaces, your likeliness to get there easily, decrease. Okay, but the bonus of this approach is that I don't need to know any analysis, nothing about the adjoint, observability, and so on. I just minimize this functional. What are you doing when you are minimizing a functional in which you are adding two terms? Well, this is a multi-criterion minimization problem, right? So this is like in classical optimization theory, you have to optimize some process, but there are some different criteria to define what optimum means. So here for us, optimum means, not too expensive control, neither nor too far from the target, because my target is to get to xt. So I need the control not to be too expensive, because if u is too large, in practice, it will not be implementable, right? On the other hand, I want xt to be close to xt. So I, penalize both of them. Adding them in the cost functional makes that when I minimize this cost functional fk, right? When I minimize it, I'm finding a good balance between the control not being too large and being close to the target. Now, what is the role of a penalty parameter K? Well, in practice, I will have the tendency to increase the value of K, right? Why? Because if I increase the value of K, rather than taking 1, I take 10, what I am doing? I am weighting 10 times more the second criterion with respect to the first. So this will allow, you know, the minimizer to be maybe a larger in U, but guarantee that I am shorter, you know, in terms of the distance to the target, right? So K large, in principle, sorry, K large will have the tendency to push down, you know, the distance to the target. Okay, that's the idea. Increase K to get the target better. Very good. Okay. Then, of course, I didn't say that because of the direct method of the calculus of variation, the minimizer of Fk is 6. Why is that? Well, again, this is a functional Fk, right? So this is a functional Fk on a Hilbert space involving the square of the norm plus another, you know, quadratic quantity which depends continuously on U. So this functional is convex, continuous, coercive. It involves the norm square actually. Therefore, it has a minimizer. So the minimizer exists. That's for free. So for every K, it's very easy, analytically at least, to build the minimizer for this problem, okay? And then what will be the expectation of practitioners of this? It will be, well, for every K, I compute the minimizer. This will lead me to a sequence UK. And then in particular, this will allow me to guarantee that the distance is smaller and smaller. Will this be true? Well, we can state the following theorem. The following says the theorem says the following. If the system AB is controllable, right, meaning that AB fulfill Kalman and all this, then this approach is correct, right? When the system is controllable, the approach is correct because then the sequence of UK of minimizers of Fk as K goes to infinity remain uniformly bounded in L2, and the corresponding controls fulfill this proximity condition. So you see that as K goes to infinity, the controls you have computed, which are approximate controls, they are not exact, they are just the minimizers UK of Fk, and K is going to infinity. These controls are approximate controls in the sense that the distance between Sk at time t and the target is going down like a square root of K. Okay, so you have a convergence, polynomial convergence of order 1/2. Fine. So this is what we wanted. Of course, this happens when the system is controllable, right? Because then, of course, if you take as U the limit of UK being bounded in L2, a Hilbert space, there is a weak limit. If you take this weak limit, then you will get, right, the exact control condition, right? So this is perfect. In case the system is controllable, you will be converging to the control. In that sense, that's perfect. But of course, in case the system is not controllable, what you will see? Well, you will see that things are not so nice, right? Okay. People will tell you this is also a bonus for this methodology, because this methodology, you can apply it always, right? You can apply it when the system is controllable and when the system is not controllable. Depending on whether the system is controllable or not, it will give you better or worse results, but you will always be able to apply it. And this is true as well, okay? Very good. Okay, now, of course, before we go to the proof, which is very simple actually, it is important to observe that when the system is not controllable, the minimizers UK of FK will be unbounded, right? And this is a must, right? So when I say that if AB is controllable, then the controls are bounded and fulfill this, right? Of course, the reverse is also true, right? Because if the controls are bounded and fulfilling this, then in the limit, you will get the controllability, so the system has to be controllable. So typically what happens is that when AB is non-controllable, the controls that you achieve when minimizing FK, right, will be bigger and bigger and bigger and will diverge, right? Why? Because, of course, the system is trying to control, and you are asking the system to reach a condition where this is, impossible to achieve, and you are asking the system to go there. Of course, if you ask the system to go to some place where it's simply impossible to get, right, then, all your energy will be burned, taking UK bigger and bigger and bigger and bigger, and actually you will never succeed, right? Okay, so now what is the proof of this very simple fact? Well, it's very easy. You say, okay, assume the system AB is controllable. If the system AB is controllable, then there is a control that I call U star that will drive the state exactly to the target, right? So here, this will be, as usual, we'll write it down here, right? I know there is a control U star that drives me to the target. In particular, you could take, right? In particular, you could take, for instance, the optimal control that we can build by the adjoint methodology, okay? So because we are talking to practitioners that they don't know the adjoint methodology, but we know. And we are doing the analysis of this more elementary methodology, right? Then we can always say, fine, if the system is controllable, I know there is a control U star optimal that I can compute by the adjoint methodology, and I know the condition is exactly reachable, okay? Now, when I come to the analysis of this model, I can say, well, in any case, if you minimize the functional FK and you find the minimizer UK, you can guarantee that FK UK is less than FK U star. Why is this? Why is this? Well, simply because UK is the minimizer of FK. And U star, even though U star is an optimal control driving me to this target, maybe for the functional FK is not the minimizer, so there is no reason why this should be as good as that. This is the optimal minimum, therefore this is below this. But now, because X star T is equal to XT, what is the value of FK of U star? This value is bounded, it's just the norm in L2 of U star. You see that this time here, right, is the U star. There is not the extra reminder of the functional FK, which is related to the distance to the target. There is not the term plus K, right, in here. The second term here, sorry, it takes too long when, yeah. The second term here doesn't show up. Why? Because when I am dealing with the sub control, this is 0, and then therefore this goes away and you lose the dependence on K, right? Okay. So this is why, in this bound, this is why in this bound, this term here is independent of K. Now, when you say that the FK of UK is less than C, FK being the superposition of two terms, what do you get? You get that this integral is less than C, but you also get that the other term, which is indeed active in FK when you minimize on UK, the second term is also bounded by C. And this leads to the two conclusions. So UK is bounded, right? This leads to the two conclusions. UK is bounded, right? And on the other hand, you know, the distance to the target goes down, right? Polynomially on K, okay? Very good. This is the direct methodology. So what happens when the system is not controllable? What is the typical situation for this? Well, you know, normally when a system is not controllable, you can always think on it, and these are, you know, rigorous decompositions. You can find that, for instance, in the book of Sontag, right? So if you give me a system, right, which is not controllable, actually, you know, this system is very much like the following, right? It will be a system in which your state, right? So X1 will be in Rn1, X2 will be in Rn2, and N1 plus N2 will be equal to N, the full dimension of the system. The system will look to something like this, right? It will look to, right? A first component where, you know, there is no control, and a second component where, you know, A to B fulfill Kalman in dimension N2, right? So it means that when a system is not controllable, you can always put it down into a canonical form in which, you know, you are controlling the second component, the component that is controllable, you are controlling it, you know, optimally, but the other component, right, is not really controlled simply because, you know, the control is not having any impact on the solution, right? The difficulty, of course, in general is that when the system is given a priori in this form, right, it's not so easy to identify in a very large system what are the components that are controllable and what are the components that are non-controllable. In order to do this, you have to reduce the system into the canonical form, right? This is like when I give you a PDE, right? And then you apply a force, and you observe that some of the components of the system are reacting in a very sensible manner. The other ones are nearly insensible. This is very hard to understand. You understand things better once you do the Fourier decomposition of the system, because then you see how the different components of the applied force in Fourier have a different impact on the different Fourier components of the system. But if you don't have this kind of canonical understanding of the system, these very elementary things are not easy to understand, right? So then, you know, this is what happens. So typically, when a system is non-controllable, right, by this methodology, you will be controlling the controllable component, but of course, the non-controllable component will remain there, right? So you see that in this particular case, when the system is not controllable, right, the distance to the target, right, the distance to the target will not fulfill this, right? Will not fulfill this because there is one component of the system that is not controllable, right? And then you will keep, you know, putting more and more energy on the system, and then you will see how, you know, things go down, right? So then you could also say that this method is also a test for controllability, right? This method is also a controllability test. Why is that? Well, because if you draw as a function of the penalty parameter K, you draw, right, the distance to the target, right, you will see that if this goes like a square root of K, this will be an indication of controllability, right? But if you see that, you know, you increase the K, and despite of this, right, rather than getting this, you rather get something that, you know, remains above a given asymptote. This will be what? This will be, you know, the manifestation of the fact that some component is not controllable, right? So this will be a manifestation of not being controllable. Okay, so we will discuss this in the after the break, but let me just indicate what we are going to do. Now, my question is, what is the implementation of the steepest descent algorithm for the minimization of FK, right? So why I am interested in this? Well, because as we have said, if I remain at a pure, in a purely theoretical level, then whenever I am dealing with a functional that is continuous, convex, and coercive, I know there is a minimizer, and I stop there. So I stop at the level of the calculus of variation. Yes, this is true. But when you are really need to control a system, you also need to give approximations of the control. And therefore, you are obliged to analyze the computational complexity of the algorithms that have to lead you to this control. What we have seen in the context of controllability is that with the correct understanding of the adjoint problem, the observability, Kalman rank condition, eventually the implementation of the gradient descent was very natural because it was just working on the adjoint, which allowed me to work in a Rn rather than in an infinite dimensional space, and then adjusting the terminal value of time capital T of the adjoint just in terms of the residual I get on the controllability condition. My question then for after the break is, how does the gradient method look when I apply it now for the minimization of FK? Of course, in principle, you know, of course, in principle, the method will look the same, will be UK plus 1 equal to UK minus some rho gradient of FK on maybe, sorry, K here is the index on the penalization, so we should call it here L plus 1, UL, gradient of UL, right? The gradient algorithm reads the same way, right? The question is, what does in practice mean computing the gradient of FK? In the adjoint methodology, we were so lucky because the gradient of J was simply the residual on the control target. What is the residual here? So the question is, what is, you know, what is the meaning of the gradient of Fk at a given U? This is what we are going to explain. Okay, so then, so you see, we have to understand what this iteration is doing, right? In the infinite dimensional space, and this is important to keep in mind, the big difference when you proceed by this very elementary method in which you ignore the theory and just apply the optimal control strategy, trying to look for the target as a consequence of a penalization and minimization process. We are working in this infinite dimensional space, okay? Anyhow, the problem looks similarly. As I said always, you can initialize the process U with L equals 0 with any U0 you like. You can take U equals 0, or you can take a control that you have out of a similar problem that you have recorded. You can take, I mean, if you know that U equals 0, I mean, very rarely will be the control you like. So you could take U equal 1, or you could take, well, anything you can think of. You could take, if you have some intuition about some oscillatory behavior of the system, you could also take the control U to be some sinusoidal functions. You do as you wish. You initialize with some U0, and once this is done, then you iterate with L, okay? So, of course, the question here is, what is the gradient of Fk at a given U? Well, because of the structure of the functional Fk, of course, the gradient of Fk with respect to U, there will be plenty of possible, say, Gateau derivatives, right? Depending on the direction you take into the space, V. Recall that V is an infinite dimensional space. It lives in an infinite dimensional space. Okay, the gradient will be the integral from 0 to t of U times V, right? Plus K, and then you will have xkt minus xt multiplying yt. What is yt? Y will be the solution of the, right, state equation out of the control V, right? Out of the control V with initial condition y0 equal to 0. So why such an structure in the, on the gradient? Oh, sorry. Why such an structure on the gradient? The reason is the following. Let's go back to, let's go back to, the functional. It was here, right? Where is our functional? So here is the functional. Okay. So what is the derivative of this functional? You see, you are computing variations with respect to U. So in order to compute the Gateau derivative of Fk at U in the direction of V, you will evaluate Fk at U plus epsilon V, right? And you will make a variation or an expansion with respect to epsilon. The integral of the modulus of U squared will become simply the integral of U times V, right? That's going to be. And then what is going to be the derivative of the square? The derivative of this square, the 2 will come and will kill the 2 in the denominator. You will keep the multiplicative constant K. The derivative of the square will be the state itself, multiplied now by the derivative of the state with respect to epsilon. Of course, the derivative of xt being the fixed target, it doesn't depend on the variation parameter epsilon. This will go away, and then you will get the variation of x. But what is the variation of x? What is the variation of x when you make a variation of u in the direction of v, u plus epsilon v? Well, the variation of x will be epsilon y, where y is the solution of the system taking the value v, but of course the initial datum for y is equal to 0. Why? Because the initial datum x0 is fixed again. So the derivative with respect to epsilon of the initial datum is fixed. And this is how, right, you will get to this derivative. Okay, very good. Now, when you look to things that way, you realize you will never be able to implement the adjoint methodology, or sorry, the gradient methodology if you do this. Why? Because you see, in order to compute the gradient of Fk, in the direction of V, you will need to compute this integral. That is easy because you have the U from the previous step. You can always take the scalar product, but you will need to solve Y for every V. And V is living in an infinite dimensional space. So even if the arrival space here, Rm, is finite dimensional, V is living in an infinite dimensional space. You could do, for instance, some Fourier expansion on trigonometric functions depending on T in order to fill this space, but then you will have a countable infinite basis. So then you will have to compute infinitely many, partial derivatives, and each partial derivative will require solving again this equation. You see that in order to compute this scalar product, I need yt, right? I need yt. And in order to, compute yt, right? You have to solve this equation. And to solve this equation, you have to do it for every v. And every time you change the v, you change the equation, you change the solution, you change the output. So you will need to solve this equation infinitely many times. Then you say the method cannot be implemented. Why? Because in every step of the gradient iteration, if I do as I have said, in every step of the gradient iteration to go from UL into UL plus 1, I will need to compute this gradient, but this gradient requires that I solve infinitely many times this ODE system. And even if this is not computationally very expensive, is the dimension of the system is not very large, even if the cost is not so high, if you do it infinitely many times, it will certainly be infinity. And then the question is there a way of making this computation, which has infinite, say, computational cost, feasible? Do you know any way of, is there any trick that allows me to make this computation more affordable? Do you have any suggestion on this? You see, this is where the adjoint methodology plays a fundamental role. So the adjoint methodology that was introduced, if I am correct, in this control context was, is the idea of Lagrange, of course, of Lagrange multiplier. But that was introduced by Pontryagin in this control context, allows not only to deal with the controllability problem, right? That was is very specific, but this is a systematic tool so that even if you are following other kind of optimal control strategies that are, less deep, but could make, the computations quite fast, they are fundamental. The adjoint, say, states are a fundamental tool also in these other potential approaches, right? So let me explain you. What is the difficulty we have here? You see, the difficulty we have here is not the computation of the scalar product of UV, right? Because if you are at the state UL and you want to move to a UL plus 1, you need to compute this gradient, right? Well, actually, what this is telling you is that, the gradient, what this is telling you is that the gradient of fk u has a first term, which is simply u, right? This is what this term is telling you, right? Why? Because, what is the, representative of a linear functional so that when acting on V, it gives you the scalar product of UV is, well, simply U. So there is nothing to be computed here, right? So I know that if I will implement this, I know that the first term, right, in here will be something like UL plus something else. My difficulty is actually the representation of this term, right? Well, the K is very simple. This is what really poses problem. Because in principle, every time I change the V, I will be changing in an implicit manner the Y, right? So you see, the V is not explicitly present here. Here I was very lucky because the V is present. So if I have to look for a representation of this linear functional, I know the representative is U because I see how U is acting on V in this way, in this case, in a trivial manner, just through the scalar product. So here, the presence of V is not explicit. And I would like to represent this product here, this scalar product, I would like to represent it in a way that I can see something multiplying V. But how can I see this? This looks like very unlikely, right? Because what is YT? YT is the solution of this system, right? In which I evolve forward from 0 up to time capital T, right? And for doing so, I have to integrate this equation, you know, accumulating the impact of V on the system along time, right? And this will be complicated because this will very much depend on the interaction of A and B. And this is actually where the controllability and the rank condition plays a role, right? So we know that the rank condition is so that whenever time evolves, you know, B is having an impact like, you know, in a trigger effect, domino effect on all the components of the system through the interaction with A. So the overall impact on V onto YT is complicated. And, you know, it will be just the accumulation of the resolution of this ODE during the time interval. Right? That's one point. It looks complicated. On the other hand, when you look to this, you say, well, but I am not interested on all the Y. I don't need all the Y. I just need YT. Not even this. I don't need all the YT. I just need the scalar product of YT with this quantity. Okay? So then the remark, the important remark is that when you look at things from an analytical perspective, oftentimes we miss the key point that can make your computations more affordable. Why? Because in my analytical mind, whenever I write this gradient, I identify the first term, which is U, right? Which is U, right? But then on the second term, what I see is that I need the state Y. But actually, if you are really computationally oriented, what you will realize that no, you don't need a state Y. The only thing you need, right? So we don't need Y. Which is a function depending on time. But just this scalar product. Okay. How can I get this scalar product? Well, you do it through the adjoint. You introduce the adjoint. And on the adjoint, you plug this terminal value. You see, this is something, yeah, not, yeah, xk, you can put xk. So meaning out of U, you solve the state equation, And then again, you see that the residual appears, right? This is the residual. What was our goal? Our goal was to drive the system to xt, so to make x at time t minus xt to be 0. This is our goal. In practice, it will not be to be 0, but it will be to be less than epsilon, where epsilon is the admissible error you have, right? And this will be your stopping criterion. So you will apply again this gradient iteration. You will apply again this gradient iteration in here, right? And you will stop at the time where xt minus xt is small enough. If it is not small enough, what I invite you is solve this adjoint system again. It's true, in principle, in this iteration here, everything was done so that I don't need to work with the states. I mean, with the adjoint state, everything was seen in the space of the states, right? I am blinded. I don't know about the adjoint state. What I tell you is that even if you approach the problem in a straightforward manner, trying to deal directly with the state problem, you will face one difficulty, which is the computation of that object for an infinite dimensional, V. And this is simply impossible to do. So even if you try this simple methodology, you will never be able to achieve this. So how do practitioners will tell you, well, it's true, I cannot compute this for an infinite number of V's, but I can do it for a few, so I compute it for a few of them. Well, yes, but then, then the methodology becomes too much heuristic. Because for which V's do you compute this? Well, people will tell you, I do some kind of polynomial expansion or Fourier expansion, and I take the first mode in the expansion, and then I compute this for a few V's. Yes, but why do you know that these are the most relevant V's, right? Actually, it's not simply about the Fourier decomposition of the matrix A, right? So it's about the interaction between A and B. And we have seen already that even in Google PageRank, right, people that were, discussing issues such as page ranking, they have to go through a bit more in-depth analysis in order to identify what are maybe the most sensible components of phi. The same will happen here, right? So if you do a too much simplified, say, projection of what the complexity of the problem is, you will get into situations where either computations are not feasible because they are infinite dimensional, or they are not reliable because they are based on heuristic projections and simplifications that are, right, not very, meaningful. Okay, so then my recommendation is anyhow, as soon as you get to this point, plug the residual and solve the adjoint equation backward. And now, if you multiply, you see immediately that if you multiply the state equation with this adjoint equation, you see what's going to happen. Let me multiply this equation by P, right? Okay? Let me multiply this equation by P. What happens? Then you get BVP, that of course you can always write as VB star P. Then you get here on the left-hand side the multiplication of P by this operator, y prime plus AY. You can play the game of the integration by parts, and you put this operator into P. It will go away. And again, you will only get the crossing of Y at T equal capital T at T equals 0, meaning that what you will get is that, the integral, you will get that the integral from 0 to T of Y prime, you will get that Y times P, the difference between 0 and T, will be equal to the integral from 0 to T of V B star P dt. And what is here? You see that, Y at time T takes the corresponding value. The value of P at time T is xt minus xt. And then on the other hand, right, at t equals 0, right, this goes away, right? This goes away simply because y at 0 is equal to 0, because this is the condition of the linearization. So you see that finally, what this tells you is that this duality can be written that way. And you say, oh, but this is extraordinary, because what did I succeed doing? I succeed doing the following. I had a complicated formula for the gradient of fk, and now suddenly the complicated part of the formula that was related to the scalar product of yt with xt minus x star, sorry, this is not x star, but is xt, right? The complicated part of the formula that was this scalar product that in principle required that I solve infinitely many times the state equation. Now this complicated part of the formula is gone and everything has been reduced to this, right? So then this term is simply the integral of 0 to t of b star p times v dt, meaning that what I have proved is that the gradient of fk at u is simply u plus k b star p. And this is the beauty of the adjoint methodology. Why? Because thanks to this magic formula, right? So this is really a magic formula. We have replaced the resolution, which in practice means running a numerical approximation of the state equation. We have replaced the resolution of the state equation for y infinitely many times for all v's in L2, 0, T, R, M, right? By just the resolution once of the adjoint equation for P. Okay? So you see that even if you are trying to solve the control problem without using the adjoint methodology, right? Is you really don't use the adjoint methodology, the implementation becomes impossible, right? Fully, because you cannot compute all those scalar products. You can solve this problem by this very key observation that, in fact, you were not interested on the whole y. So this is a goal-oriented computation, right? So this is a goal-oriented computation. A goal-oriented computation is that, so traditionally, you know, for partial differential equations, people will tell you, okay, if you have to solve the Laplace equation, then you apply finite elements, and then you will have an approximation of the solution of the Laplace equation. Goal-oriented is when often, in the context of optimization theory, you are not interested on the whole solution. You only need some features of the solution, maybe the trace somewhere, the average into a subset, some trace of a piece of the boundary, some values in some interior points where, you know, your sensors are located, and so on. And the key contribution of adjoint methodology is that when you don't need the full solution of the Cauchy problem, but you are just goal-oriented because you want simply some projections of the solution, then you can use the adjoint in order to reduce dramatically the cost, right? And then you see that finally, in the gradient iteration of the minimization, direct minimization of fk, what we have succeeded is to reduce the computational complexity to the previous analysis of the controllability we have done. Why? Because in every time step, you have to solve, of course, the state equation, right? And you have to solve the adjoint equation, and that's it. So in every time step, in every step of the gradient descent iteration, the computational cost will be similar. One resolution of the adjoint, one resolution of the state, right? Okay, very good. And once you have done that, then you see that the algorithm then can be rewritten something like UL plus 1, right, is equal to UL minus rho, and this rho is simply UL plus, sorry, there was not, yeah, there is another K here, K, B star, B, L, okay? So what is the stopping condition here? The stopping condition here will be when you are at the minimizer, right? You are at the minimizer whenever the gradient of fk is equal to 0, and the gradient of fk, so the minimizer, right? In this case, the minimizer is when the gradient of fk at u is equal to 0, and this is equivalent to u plus k b star p is equal to 0. And this is equivalent to B star P is equal to minus U over K, right? Okay, and this is when this is equal to 0. Okay, well, that's what I wanted to show you. Okay, so the conclusion is that the adjoint methodology, even when you think you don't really need it, is actually something that can be extremely helpful in your resolution of the control problem, whatever the strategy you have adopted is. And with this, let me now go back to, do I have it here?
Professor. Hi, Professor.
Yeah?
You screening your photo. You share your photo.
Yeah, I know. I am now looking for the new slides I wanted to show you, but I have so many here. Sorry, give me a second.
Oh, sorry.
I have to find them. Yeah.
Take it easy.
I think, yeah, I have to transfer them. I think they are in my computer, but not in the iPad. Just a second. These are the slides I sent you. Yeah. Very good. So in the meantime, if there is any question, please let me know. Okay. 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 Yeah, so that's a good comment. So can we represent delta FKU as a function in L2? Yes, you are totally right. Right. So this is actually what we are doing. If you check what I have said, this is a very good clarification. Thank you. What did I do? Right. Well, I have to share the slides. What did I do? I said that the gradient of fk at u, u is the control. U is in L2, 0t, Rm. And then what I have said is that the gradient of fk at u is u itself, which is, of course, right, an element of L2, 0t, Rm, plus a small piece, which is a constant k, right? So this is a constant times b star p. But what is b star p? B star is a matrix, right? M times n. So it's taking the adjoint solution P, right? Which is living, right? So P lives in L2, 0t, R, n into, you know, LP, 0t, Rm. So this is an identity in L2, 0t, Rm. So all this adjoint methodology is fully coherent because, you know, you decided to work, right? You decided to work in the space. You decided to work in the space of the controls, right? Minimizing this functional. And then all the gradient methodology together with the adjoint methodology is coherent and leads to a very nice iteration in that space. Yet, of course, you are in the infinite dimensional context, okay? But at least what we have succeeded is that despite, you know, the fact that you are in the infinite dimensional context, the running of the algorithm is computationally as expensive as the ideal adjoint algorithm for controllability. Why? Because in every step of the gradient iteration, I'm just applying, right? I'm just needing one resolution of the adjoint equation and one resolution of the state equation. Okay? But as I said, if you will not know this adjoint methodology, and you formulate the gradient descent algorithm directly in this infinite dimensional context, this will be hardly feasible, right? Because in particular, you will need to solve the state equation as many times as possible controllers there are. So this is complicated in ODEs. Imagine when you are in the context of a complex fluid dynamic simulation involving Navier-Stokes, and then in every step of the time iteration, you need to, of the gradient iteration, you need to solve the state equation many times corresponding to the all possible choices of the controls. This becomes rapidly unvisible. Okay, very good. Okay. Okay, so now let me, do you see the slides now? Sorry, do you see these slides now?
Yeah.
Okay, so let me go back to the topic of machine learning that was that we discussed the first few days as an extra motivation to control theory. We said control theory originally was motivated by classical problems in engineering, also in mathematical biology, in social science, and so on. And then develop a number of tools that nowadays we see all reflected in the context of machine learning, where problems are very similar to the classical ones in control theory, except that they are now characterized by being all in huge dimension with an incredible large amount of data and extremely complex, you know, computationally, right? But that we can address thanks to the fact that nowadays we are, right, able to run massive simulations thanks to modern computers, right? Okay, so we said the other day, when we do, when we are in the context of machine learning, right? In particular, you know, neural network approaches to machine learning, there are two functions. I mean, there are some functions that play a crucial role, right? So these functions that are called sigmoids, right? Okay. Sigmoids, in some sense, they are all approximations of the Heaviside function, right? We all know the Heaviside function. We know, for instance, that the derivative of the Heaviside function in the context of distribution gives you the Dirac delta, right? So it's the primitive of the Dirac delta, for instance, the Heaviside function, okay? Okay, we know that a linear combination of Heaviside functions allows you to build all kind of piecewise constant approximations of any functions, right? So even though the Heaviside functions are discontinuous, they are very nice objects in order to reach density, right? Because, you know, just piling up, piecewise constant plateaus in a fine scale, you can really approximate any function regardless how complex, right, the shape is. We see it also reflected here. And this was actually also the basic idea on the, you know, the intuition of Riemann about, you know, the Riemann integral. Riemann said, well, integrals are about computing areas, and the area of a given surface underneath a given curve or a given graph, right? The volume, whatever the area, the dimension of the Euclidean space dimension you are considering is, you can always write it down in pieces, you know, by, you know, computing integrals of rectangles, right? Which are given as graphs of piecewise constant functions. Very good. Then sigmoids are just approximations of that, right? So this is particularly clear if I take the sigmoid function, right? If this is the sigmoid function, and I do here if I do here sigma, if I do here sigma x over epsilon as epsilon goes to 0, this sigma x over epsilon converges to the Heaviside function, which is 0 on one side and 1 in the other. Okay, very good. So this is more tricky, right? In the sense that this will not give you, right, as limit, right, the Heaviside function. This will give you actually a function that is just defined on the left-hand side, right? Because it will give you, if you make this scaling sigma x over epsilon, what you will get is this slope higher and higher, so that eventually you get this function which is 0 on the left, right? But you see, this function is also interesting, right? And we will analyze this with more detail later, right? Because even this function that is simply 0 to the left and nothing to the right is something that could be useful, right? Because it allows you to, you know, divide the space into two pieces and treat very differently one and the other, right? Okay. So this is like, you know, when you have you are lecturing, you know, calculus class in the first year, you know, bachelor diploma at the university, there are 200 students. I mean, the class is very large. Then you do the theoretical class, you know, once per day or so. You do it in a large auditorium. You do it for 200 students. But then when you want to really that the students practice and get into the details and work harder in order to better understand and master the topics, then very often you take these 200 students, you divide them into 10 groups of 20 people or 20 groups of 10 people, and then you do some practical classes, you know, solving exercises with these smaller groups. Of course, for this, you need many more other people helping the professor to coordinate all these small classes, right? So this is a traditional way of learning mathematics. You do an auditorium lecture with the key concepts, and then you divide. This is what, you know, the sigmoid allows you to do, right? In particular, the ReLU, this is the so-called rectified linear unit, you know, by scaling, you see that allows you to, you know, to just decide 0 on this group, okay, which means that you can focus on that group or on the others. Okay, very good. So what is the connection? We said one of the traditional problems in machine learning is supervised learning, we said. And supervised learning is just assigning to every item, you know, a label. So how can we relate this with the sigmoids and with the control theory? So this is the one possible way of doing it, right? So there has been some recent, some traditional work you see, like people like Sontag and Sussman. After the first paper by Sivenko was written about the density of neural networks, they, analyze the controllability of some systems involving the sigmoids. This methodology has been revisited like 20 years later, in particular in the works by Wayne Ani and collaborators, in which, the interface between control theory and machine learning has been revisited. And this is also a topic to which we have contributed, in which we have written 2 papers that are indicated down here and that you can find in arXiv, right? They are publicly available, you can download them. The idea being the following. Okay, so Sivenko said that by combining, sigmoids, you can achieve all kind of approximation results. Any function can be approximated that way. Well, out of this idea, there are several possible variations. One of them is the so-called residual neural networks, right? Residual neural networks. What are the residual neural networks? Well, there are very simple objects, right? So you consider a state X living in some space dimension RD. You see, it's like in the control theory. This is why I devoted so much time to explain the control theory in the linear case, right? Because it looks like we are repeating again and again the same kind of problems and concepts. This looks like very particular, but once you understand that, you are prepared to do huge jumps and get into, other fields with the same methodology and ideas and to perform well, right? So this is what residual neural networks are. The definition is the following. You just take a state in RD. So you are in the D-dimensional Euclidean space. The dimension of this space can be huge. It could be thousands of millions when you are talking about internet, for instance. It would be less if you are in the stock market or if you are just looking to, I don't know, some parameters on the city you are living. You talk to the city hall and the city hall, will tell you, well, we are interested about the well-being of our citizens, and we are considering these 40 parameters, right? So one being, how, clean is the town, or how clean is the air people are breathing, or how, light and efficient is the traffic or the public transport. So 40 parameters. So you can be in dimension, low, intermediate, or very high. It doesn't really matter. And then what a residual neural network is just a discrete time dynamical system in which you move from the, say, step k into k plus 1 in an incremental manner, in a residual manner. This is why it's called residual, right? Because I'm taking the state x and I am making an additive variation of x through a sigmoid, right? A nonlinear function of x, because it's involving a sigmoid function, right? But with a small amplitude. So h is small, right? This h is small. Okay, so I'm making small corrections. You could say, well, when you make small corrections, you are being very slow. You prefer to make big jumps to be successful and to succeed faster. Well, you can try, but these things are tricky. So our recommendation, and this is the point of view of residual neural networks, is you better do it carefully by small steps, and only when you are guaranteed that you will succeed, you revise your methodology to learn better, to make it maybe in bigger steps, right? This is what we did also with the gradient descent algorithm, right? What we said in the gradient descent algorithm was, if I take rho small, smaller than alpha over m, according to the condition number of the matrix, when I take rho small, I can guarantee the convergence of the methodology. And once you understand the methodology, then you say, oh, then I can take rho a little bit bigger, either, you know, carefully chosen according to the Hessian, or I can do some kind of bisection algorithm in order to move very fast and only go back a little bit when I see that the functional is not going down, but it's going up again. You know, I could even use, you know, the multi-step gradient algorithm in order to accelerate the convergence. There are many things I can do a posteriori. But before anything, what I did was to analyze the simplest possible gradient descent algorithm, which is the steepest descent. So here we adopt the same methodology. There are many things you can do fantastic with neural networks, but maybe before anything, you should first understand how to manipulate a neural network in an incremental manner, and this is what the residual neural network does, right? So a ResNet, which is the abbreviation, sorry, for the residual neural network, right? A ResNet, right, is just what? It's just a time discrete dynamical system in which the contribution of the sigmoid, right, which is the neural network, is incremental or residual, right? In the sense that it's just a small correction of the identity. Okay, very good. And then people said, in this way, you can generate a discrete dynamical system. What is the goal of this discrete dynamical system? As we said, I mean, the very simplest application is this, you know, supervised learning paradigm, right? In which the goal is simply, you know, to classify items and place every item on the corresponding, say, label or basket. So what are we doing in this case? Out of the initial data, we have built a dynamical system that little by little will cross all the possible trajectories. We were doing this drawing the other time, right? We said, okay, I have red points, right? I have blue points. I have green points. I have purple points, right? And they are all mixed. Okay. And what I want is to build a dynamical system that is taking the red, all the reds, you know, go to the corresponding location. All the greens will go to the corresponding location, right? All the blues go to the corresponding location, okay? And then they are grouped into different, say, categories, right? This is the goal. And then by, you know, this residual neural network paradigm, my aim is to see whether I can build these discrete dynamical systems in a way that this task is performed well. And what is the aim? Well, the aim is that once this discrete dynamical system has been correctly, properly designed, I can use this discrete dynamical system for generalization, meaning that every time, you know, tomorrow, the next day, and so on, you will bring me a new item, right? Then this item will be put in the dynamical system, and the dynamical system should tell me where this item should go. So you have built a machine that is able to classify data without your further intervention. Of course, this doesn't mean that as a human, you have not to work hard. In fact, we are working hard. We are working a lot in order to design this dynamical system, right? But once the dynamical system is designed properly, then you can stop working, turn on the engine, and then every time there will be a new datum, this datum will be mapped to the corresponding destination, right? Okay, it will become an automatic distributor of data. Very good. So then you see, in principle, this is a time discrete dynamical system. But if you think that this parameter h, which is regulating how large your, incremental nonlinearity contribution of the sigmoid will be, and we have learned from a steepest gradient descent algorithm that it's better to first learn with small variations to later try to optimize the amplitude of the jumps, right? If I think on h being small, right, like, of the order of some delta t, you agree with me that here, what I'm doing is actually, I am writing a time discretization of this ordinary differential equation, right? And this is what is called a neural ODE, right? This is what? This is an ordinary differential equation that I call neural because the nonlinearity that is driving this ODE is this sigmoid in here, right? And this sigmoid could be either the smooth one or it could be the ReLU one, right? You see that, this is very nice because the ReLU, we have said, well, this is a kind of singular function, right? It's not as smooth as, the classical arc tangent sigmoid is. This is, there is a peak here, right? And this nonlinearity sigma here, right? It will enter into the neural ODE. But despite of this, right? But despite of this, you know that this neural ODE is going to be well posed, right? Because what is the regularity conditions I need on the sigmoid, right? What are the regularity conditions I need on the sigmoid to make the Cauchy problem for this ordinary differential equation well posed? Do you have an idea? Do you remember from your course in the bachelor program? What is the condition you need in the nonlinearity to make an ordinary differential equation well posed? Is Lipschitz continuous? Thank you. This is true. A nonlinear ordinary differential equation, the most classical result, which again, by the way, is a consequence of Banach fixed point iteration, no more than that, right? The classical theory of Cauchy-Lipschitz for ordinary differential equations guarantees that when sigma is globally Lipschitz, the ordinary differential equations is well posed, meaning that you give me any initial datum, xi, and then, right? So for each, right? Initial datum, xi, right? In RD, there exists a unique solution, x, which is continuous, right? With values in RD is even, C1 when sigma is Lipschitz continuous, right? And this sigma here, the ReLU, is precisely Lipschitz continuous. Of course, it's in the limit of being Lipschitz, right? In some sense, piecewise linear with angles, with jumps on the derivatives, is the most you can allow in the Lipschitz class, right? So you see that maybe this is smart overall, right? Because you see, if I consider all the class of possible nonlinear dynamics, right? the dynamics generated by the ReLU are extremal, right? And this reminds you of these classical theorems in optimization theory that tells you that, well, when you are minimizing, for instance, a convex function on a polygon, the minimum is achieved always on extremal points, right? Okay, so in some sense, we are saturating, when considering the ReLU, we are saturating the possibilities that ordinary differential equations offer, right, for achieving, say, interesting dynamics. Okay. On the other hand, as we have seen when we were presenting the result by Sivenko, all the density argument by Sivenko was based on the fact that you can regulate the B, which is where is the center of gravity of the sigmoid, the A, right, which is orienting, the interface of the sigmoid, because this is written in 1D, but we are in multi-D, right? So this point in multi-D will become an equator dividing the space into two, right? How do you orient this equator? And the W is also a matrix which allows you, in the case where you are solving vectorial systems, is orienting the action of the sigmoid in a space, right? Now, of course, in the context of the density theorem of Sivenko, where you are just making linear combinations of finitely many of these sigmoids, right? These parameters depend on the discrete parameter K, right? This B, A, W depend on the discrete parameter K. When you move into the time-dependent context of neural ordinary differential equations, these parameters depend continuously on time. And you say, oh, but then this is like a control problem, right? Because what is the goal, right? What is the goal? The goal is to, so maybe I can add one page here. Okay. So what is the goal? What is the goal? The goal is, given now this right, neural ODE in the time interval 0t, knowing that xt, the state lives in Rd, that bt, at, and wt can be chosen as controls, right? The goal is that given a family of initial data, which can be capital N, these are the data to be classified. You see that capital N has nothing to do with the dimension D, right? N and D have nothing to do. D is the space dimension in which the points are moving. If they are simple objects, if you are just dealing with, you are just, helping kids to put order into, into the game room, and you have balls of different, say, radius, then you say, okay, the small ones go to the left and the big ones go to the right, and you order these, soccer balls just by the size, then each ball simply belongs to a one-dimensional space where you will simply look to the size, right? To the radius, right? And then, your objects will be, in that case, will be simply living in R. You are just taking into account the radius. But when you are classifying pictures in your computer, every picture is given, by plenty of pixels, right? Then the dimension of the space is, as big as the number of pixels that the resolution of the picture you have allows, right? So then this will be in a very huge dimensional space, right? So then the D is just the complexity of the objects you are classifying, right? You take into account one parameter, size, or you take two parameters, size and color, but maybe you take into account many other parameters because maybe you are dealing with polygons of different colors, of different sizes. Then you have size, then you have color, but you have also shape, right? Then you can be increasing or diminishing, you know, the space in which the points to be classified, the items to be classified live. Okay, very good. But then, you know, the number of points to be classified has nothing to do with the complexity. You could have just 10 photos. So 10 photos means that n is equal to 10, very few. But the photo is a very complex object with a very high resolution. It lives in a high dimensional space. So you could have few items in a high dimensional space. By the contrary, you know, you get to the soccer field and the soccer field is full of, you know, football balls of different dimensions. So in that case, you are just paying attention to the radius, right? And then D is equal to 1. But the soccer field is full of soccer balls. So they are different sizes, but the field is full. So there are thousands of them. So N is of the order of thousands. So you could also be in the situation where D is very small, but N is very large. Or you can be, you know, in modern applications of machine learning, like, you know, bioengineering, face recognition, language recognition, many other possible applications in which both D, the dimension, is high, and N is also high. N is high because you will have plenty of data to try to classify and understand, and D, the dimension, will also be very high, right? Because, you know, for instance, when you are translating from one language to another, that you can do, for instance, with this software DeepL that you can download, right? Deep learning, right? DeepL. Then you are dealing with objects, so, you know, grammatical constructions, which are very complex and therefore live in a high dimensional space. So all possibilities are there, right? But all of them are included in this paradigm. D is the dimension, right? And N is the number of items to be classified. And then what is the goal? As I said, the goal is that, you know, you give me this neural ODE, you give me all the possible initial data, right? And then to every initial data, you allocate a label, right? Li, right? But this label typically will live in a space of different dimensions. So, I mean, it will be just M of them, right? Meaning what? Meaning that, for instance, when I am, you know, dealing with this cloud here of blue points and red points, you see, in this case, what are we doing? We are considering points on the plane, and we are distinguishing them by colors, right? So I'm just in two space dimensions. I am dealing with one extra feature, which is the color. So what I'm doing, I'm working in R2 because points are placed in different locations. I have many of them, plenty of them. So N is very large. So D is 2. I am on the plane. D is equal to 2. N is huge because there are hundreds of points in this cloud, right? And there could be many more. But then I have only two labels, right? The blue and the red, right? So there are two labels. So then, and my goal eventually will be like in a soccer field, that the blues go to one side and the reds go like to another, right? Like in the final of the Europe Cup we had recently. So you have all these ingredients, right? And what is the goal, right? And as I said, the goal, right, is that WT, AT, and BT are so that, right, the solution X, right, X, which of course differs whenever, you know, I change the initial datum, right, will, right, go to the class that corresponds to it, right? This is the goal, right? So here we should say that for every I have an Li, which actually will be one element. I should say that Li should live indeed in, maybe in order to improve a little bit the notation, right? I should say that for every I will allocate here some Mi, right? And is this Mi, right? Is this Mi that lives in the space of labels, right? So then the goal will be that whenever I solve this neural differential equation with the strategically chosen controls, the solution will be so that it belongs to the part of the space which corresponds to the corresponding label, right? So then in practice, I'm doing what? I have initial data, red points, right? And blue points. They are all mixed. Okay, like in our society, you know, junior people and elder people share the same building, right? So then you could say there are the kids, there are the, you know, the young people, there are the senior, and then there is the very senior people, right? So you could stratify in 4 categories. Or you can say there are ladies and there are men, right? So you can classify in 2 other categories. There are many ways you can classify people, right? So here is just a matter. We have classified people, you know, according to 2 different colors, whatever it means. And then what I want to do is that at the arrival, right, for instance, I like here the blues, and I like here the reds, right? And then what I have to do is to build a dynamical system so that starting from this initial configuration, right? So this is the initial configuration at t equals 0. At t equals 0. And this is the final configuration at t equal t. My dynamical system, right, which is given by, you know, this formula here, x prime of t equal w t sigma at xt plus bt. This dynamical system that is generating this machine that transform t equals 0 into t equal capital T as the solution, as the Poincaré map, you know, mapping initial data into final data. This machine is able to bring me, you know, from blue always to some point on the left, right? I'm not being so demanding as I am in the controllability problem, right? Because you see, the only thing I am asking to this map is that the blues go to the, you know, to the left hemisphere, but then the reds, right, go, you know, to the right hemisphere, right? Okay. So basically what I'm doing, another different way of writing all this will be that the set of initial data, right, is classified into 2 classes, right? So there are the initial data corresponding to, you know, 1 to N1, and then the initial data that are N1 plus 1, right? N1 plus 1 up to capital N, so that, you know, when I look to the real part of the solution of the ODE at the final, I mean, when I do when I'm saying the real part, I mean, yes, I mean the projection into, you know, left and right. When I look to the real part of xi at time capital T, this will be less than 0 for y from 1 to n1, but the same real part will be positive for I equal to n1 plus 1 up to n, right? So you see that from the perspective of control, when you look to this problem, you say, well, is this problem harder or simpler than the classical controllability problem? Well, it depends, right? Because if you look from a controllability perspective, you say, well, the problem is not so precise, right? In controllability, I like to go from an initial condition to a final one. So here I am relaxing this terminal condition a lot. I don't need to get to a specific location. It's sufficient to be left or right. Yes, but from a controllability perspective, it is true also that the problem is very, very difficult to solve, right? Because now with the same ODE, with the same neural differential ODE, with the same controls, I have to be able to control all the trajectories simultaneously. And you see, this will be an impossible task for linear problems, for linear models. Indeed, assume that you consider two things, right? Assume that you consider the linear differential equation, right, that we were discussing the previous days. But now you say that, okay, I have a family of initial data, and then I give also a family of targets. I give you the family of initial data, and I give you the family of targets. The question is, do you think that there will exist an X IUT so that all the solutions of this problem will get to the corresponding location for all possible values of the indexes of the index I? So this is, of course, what people call often in the literature simultaneous control, right? That would be fantastic, right? Because then, rather than, building the controls, right? Rather than building the controls here, so that, for every trajectory, I have one different control. Whenever you give me an initial datum and a target, I compute a control. Then I will have a magic control that is able to take all these, different initial data, allocate a different target for every initial datum, and then there will be this magic control, right, that is able to take all of them simultaneously, driving them to the corresponding location. If I was able to do this in the linear setting, this will be extraordinary, because I then will apply the tools we have already analyzed. I will not need to get into more complicated things, arising in the nonlinear context of neural networks. But my claim is that in this linear context, you will never be able to do this. Could you please tell me why? Why in the linear context this is hopeless? You will never be able to solve the task that you are facing in the context of data classification or supervised learning in the linear context. I need to move into the nonlinear paradigm. Why? Why do you think this is a must? Okay, so I give you the reason. The reason is basically the variation of constant formula. The variation of constant formula makes computations very nice, but it also limits, shows you why you are very much limited, right? So the variation of constant formula says that whenever you take an initial datum, this is the solution of the problem. Now we are looking to the solution at time capital T. Okay. And then you see, when you choose U, right? If U is such that starting from the first initial datum to be classified, you get to the corresponding target, this already means, right, that you have chosen, right, the control so that, you know, you are filling this gap, right? Right? So this is already given. So you see that, you know, the impact of the control, because the system is linear, the impact of the control on any possible initial datum you choose for controlling is just an added increment. But this added increment is fully determined just by the control of the first initial datum to the corresponding destination. So what the control is doing, right? What the control is simply doing is out of the initial cloud, right? Out of the initial cloud, you look to the free dynamics, right? And this will give you another cloud. Of course, in principle, there is no any reason that the free dynamics will mix, I mean, will separate beta. I mean, if you run a kind of harmonic oscillator of a diffusive process driven by a linear differential equation, this will take initial data that are mixed. It will change the, you know, the morphology of that set, but eventually you will get a different cloud which is mixed. And the control, right, is simply an additive translation. So you will be moving, right, this cloud to a different location, but you will definitely preserve the same amount of mixing. So then forget it. In a linear context, you will never be able to solve the tasks that supervised learning or data classification are requiring. And this is why we need to move into the nonlinear setting. And in this nonlinear setting, we choose to work with the sigmoids and in particular with the ReLU, which is Lipschitz. And in some sense, it allows you to explore the most possible, sophisticated, most possible scenarios in nonlinear control, because you are into the extremals of the borders where the theory of nonlinear differential equations applies, okay?